Okay, so this is 6-1. Here's example 2B. Pause the tape, write it down. Some things to remember. At the end, we've got a weak acid that's conjugate base. That's a buffer solution. Plug in your equation. When the concentration of these are equal, that's log of 1, which is really 0. So you get pH equals pK. There we go. That's what next year is. All right, so example 2, part D. Go ahead and start working this one out on your own. I'll write it down up here, but go ahead, get started on it. All right, for the stoichiometry step, we've got 40 milliliters of 0.1 molar acetic acid, which is 4 times 10 to the minus third moles. For the sake of the table, we're just going to call it 4. Hydroxide is 30 milliliters, so 0.03 liters. Also 0.1 molar. We're going to call that 3. Water, leave it out. Initial acetate concentration 0. These are used up in a 1-to-1 ratio, so we're going to use all of the hydroxide, which means we're using 3.0 of the acetate, acetic acid. Here's our number of moles. We need to change this to concentration. So in this case, lost my spot. Yep. So it is important that rather than just sticking the moles into the Henderson-Hasselbalch equation, we actually find the concentration this time. Again. Yep. And our total volume of the solution here is 0.07 liters. We also find our acetate equation. Here we have a weak acid and its conjugate base left, which should trigger this in your head. To find the pH, it's the Henderson-Hasselbalch equation, not equals, plus plus the log of the anion. Try that again. You'll notice something about this particular acetic acid. Its pKa has been the same every time. So in this situation, I've already calculated pKa several times. And so I really don't have to do it again because the Ka stays the same, so the pKa stays the same. Plus the log of 4.3 times 10 to the minus 2 over 1.4 times 10 to the minus 2. This will tell me the pH of my final buffer solution once it reaches equilibrium. And we should have this one calculated. So weird. What do we get? Get the wrong answer.
Why do you change the
Change what?
What you do weird?
Because this is in terms of concentration. Because the last one, the numbers were the same whether it was moles or concentration. They were equal amounts. This one very likely would have worked out the same if you used moles, but I wanted to show you that this is specifically concentration, which is molarity. But their volumes are the same, yeah.
I got 5.22.
Okay, good.
So it works the same as the moles or the
Then
concentration.
it does work the same. What did I do?
What did you do?
Well, I got 4.25 when I did concentration. Well, yeah, wouldn't it work the same because you're multiplying and dividing them by all of the same numbers?
Yeah.
Okay,
So-
so that's what I got the first time.
Okay.
So the next one's interesting.
I guess I can.
Yeah, either way, you're going to get it 5.22, 5.23, something in that range. So, okay.
Yes, you can. Okay.
So we are looking at part E, and this time we've added 40 milliliters of the sodium hydroxide. So I'm going to rewrite the reaction again. Okay, so our concentration here has been the same the whole time. Number of moles has been the same, so 4 times 10 to the minus 4th. This time, for the sodium hydroxide, it is 40 milliliters times 0.1 molar, which makes it this number. So we have equal concentrations of our reactant here and no conjugate base at the beginning. Okay, so at the end of the stoichiometry step, first off, both of these are the same, so you're going to subtract out 4 from both of them. There's none of the weak acid, there's none of the hydroxide. And everything here is going to be the conjugate base. So your concentrations here. Your concentration of the acetic acid at the end of the stoichiometry step is 0 molar, and your concentration of the conjugate base we have a total volume of 0.08 liters. Five times 10 to the minus 2 molar. Here's probably why you're confused. If you're trying to use the Henderson-Hasselbalch equation here, it won't work because you're trying to divide by 0. It's not a buffer, which means no Henderson-Hasselbalch equation.
Oh, yeah.
David Hasselhoff is the
David Hasselhoff.
So here's the step you have to do, the equilibrium step. And we have a basic solution this time. And so we have to flip this around for the equilibrium step. This one's kind of a pain. You run out of room? Two ice tables in the same problem is not the most wonderful thing, but sometimes it happens that way.
And we're flipping it because we can't have 0 on the bottom, correct?
So H2O, we're going to ignore. This we just found, its concentration was 0.050. This is 0, this is 0. And this is where we actually have to start filling in the X's using the KB value and the equilibrium expression. Excuse me. So Kb equals the concentration of hydroxide, the concentration of this over the anion. We don't have the Kb, but we have the Ka, so we can pretty easily find KB. So the KW, 1 times 10 to the 14, divided by the Ka, 1.8 times 10 to the minus 5th. So 5.56 times 10 to the minus 10th is the KB. Equals X for the hydroxide, X for the weak acid, 0.050 for that acetate. And remember, we are not putting this in the equation. So you should get an X of something like 5.3 times 10 to the minus 6th. And X, that's telling us the hydroxide concentration as well as the weak acid concentration. Make sure you put molars here. So we want to know pH. There's two ways you can get to it. You can do pOH and subtract that from 14. Or you can use the KW. Yeah. So either way, you're going to get a pH of, and I think I heard it correctly, 8.72.
What was the KW?
Huh?
What was the KW?
That's where, remember, KW is the concentration of hydrogen ions times the concentration of hydroxide ions. And so we would solve for H plus here and use that to find the pH. There's a note here. This is the point. Write this down. This is called the equivalence point. And on Monday, we'll see on the next page what this means. The equivalence point is really important for our lab next week. And we want to get it to this point, and then we'll go past it. But we want to measure the pH at this point. It's going to tell us a lot of stuff. But that's on the next page, and that's going to be the next class period.